Hi to all. Now I am going to continue the electrostatic potential and capacitance. In the last class we discussed about the capacitance of parallel plate capacitor without dielectric, with completely filled with the dielectric and partially filled with the dielectric. That topic is completed, and you know that, for example, this is a capacitor. Every capacitor has two plates, and if the separation between the two plates is air or vacuum, at that moment the capacitance formula is epsilon naught A by D. If the space between the two plates is completely filled with the dielectric, completely filled with the dielectric, at that moment the capacitance formula is K epsilon naught A by D. If the separation between the plates, D is the separation between the plates, and now a dielectric slab of thickness small t is introduced between the two plates of capacitor, at that moment the capacitance formula we derived as epsilon naught A by D minus T of 1 minus 1 by K. These three formulas we know. This is capacitance of parallel plate capacitor without any dielectric. In between the two plates there is vacuum or free space. Here the two plates are filled with a dielectric, completely filled with the dielectric. Then the capacitance become K epsilon naught A by D. Now for example, the space between the plates is partially filled with a dielectric substance of thickness small t, then the capacitance formula is epsilon naught A by D minus T of 1 minus 1 by K. And that we discussed. These three already we discussed. Now if the case is like this, there are two different dielectric slabs are there, and their dielectric constants are K1 and K2, and the separation between the two plates is D, and half of the separation is filled with the one dielectric slab whose dielectric constant K2, and the remaining half of the separation is filled with another dielectric slab whose dielectric constant K2. Then what is its capacitance? Here we know the capacitance, here we know, and now we are going to find out the capacitance in this case. Then how to find out the capacitance, right? And let us see. It was very simple to find out the capacitance, and the last class we also discussed the series and parallel combination of capacitors, right? Series and parallel combination of capacitors, and the resistors and capacitors series parallel combination somewhat different it will be there. In case of parallel combination, in case of parallel combination, all the positive terminals, first terminals of capacitor are connected to one point, all the first terminals are connected to one point, and all the second terminals are connected to some another point. Then the capacitors are said to be in parallel. All the first terminals connected to one point, this point. Second terminals of all capacitors are connected to another point. This is the first plate, second plate, first plate, second plate. All the first plates are connected to one point. All the second plates are connected to another point. Then the capacitors are said to be in parallel combination, and C1, C2 are the capacitance of two capacitors. Then the effective capacitance in parallel combination is C1 plus C2. But in series combination, then we got C1 C2 by C1 plus C2. And now here we have to split this into two capacitors. How we have to split this into two capacitors? And this we have to split into two capacitors with the help of like this. Here, look at here, up to this place. Here we can consider as one capacitor, and this part we can consider as another capacitor. No, not like that. Look at here, and this part is considered as one capacitor, and this part is considered as another capacitor. Now let us see, and I will redraw this diagram like this. This is the plate area is A. Plate area is A, and first dielectric substance is, right, what is that? K1, whose dielectric constant, right? And this we can take as the first plate, and the next one is this capacitance we can consider as C1, and now another plate, this one, up to here one capacitor, up to here one capacitor, and now this is the another capacitor we will take, and here capacitance we can consider as C2, and the second dielectric constant is K2, and this is positive and this is negative, and here positive and this is negative. There are, now we split the one capacitor into these two capacitors in order to find out the effective capacitance easily. And now these two capacitors, and this is positive, means here negative will induces it here, and this is positive and this is negative. And now these two capacitors are in series combination. This is the first plate, second plate, and the first plate and second plate. Now when we say that the capacitors are in series combination, this is the first plate and second plate, and the next first plate, second plate. Second plate of first capacitor connected to the first plate of next capacitor, and so on. Then the capacitors are said to be in series combination. In series combination, the effective capacitance formula is C1 C2 by C1 plus C2, or 1 by Cs is equal to 1 by C1 plus 1 by C2. That we know already. And now let us see that formula we have to use to find out the effective capacitance in this case. And for that, first capacitor capacitance formula is what? C1. C1 is equal to K epsilon naught A by D formula. K is K1, epsilon naught. Area of plate is A. Area is not changing. Only separation is changing. Here separation is what? D by 2. And here the separation is D by 2. Why? This part is D by 2 and this part is D by 2. That's why. Epsilon naught A by, okay, area is not divided here. Separation is divided. D divided into D by 2, D by 2. Epsilon naught A by D formula होता है. Capacitance formula is epsilon naught A by D. What is the formula for the capacitance? K epsilon naught A by D. And here K is K1. K1 epsilon naught A by D. And C2 formula is what? Similarly, C2 we will write. C2 formula is K2 epsilon naught A by D. And now we got the C1 and C2. Next, we have to find out the effective capacitance. For that, we have the formula for the effective capacitance in series. Now let us continue. Actually, I was thirsty. That's why I drink some water. Now let us see. Continue this one. These two capacitors are in series combination. In series combination, effective capacitance formula is C1 C2 by C1 plus C2. Now we have to substitute C1 C2 formulas. Right here we got K1 epsilon naught A by D into K2 epsilon naught A by D. Right. And here separation is what? Separation is not D at here, right? Here K is K1, epsilon naught is the permittivity, A is the area of the plate is A here, and here also A. Okay. And but the separation here, separation between the two plates is D by 2. That's where here we write as D by 2. Then this will become 2K1 epsilon naught A by D. And here the same thing. The second plate separation is also, second capacitor separation is also, plate separation is also D by 2. That's where we will get again 2K2 epsilon naught A by D. And now let us see, we can substitute these two formulas in above equation, in this equation, and then we will get C1 C2 by C1 plus C2. C1 formula is this one, C2 is this one. Here from here we will get, and C1 plus C2, C1 plus C2, 2K1 epsilon naught A by D plus 2K2 epsilon naught A by D. And now CS is equal to, here we have to simplify. For that, 2K1 K2 into epsilon naught A by D into epsilon naught A by D by, this is here epsilon naught A by D we can common, 2 epsilon naught A by D we can common it here. Then we will get here K1 plus K2 we will get, right? Here 2 epsilon naught A by D common means K1 remains, here K2 will remains. And now let us, something will cancel, epsilon naught A by D, and then finally we are getting the effective capacitance as 2K1 K2 by K1 plus K2, right, into epsilon naught A by D. This is the formula for effective capacitance. Okay, and in this case the effective capacitance is this one, and if it is equal to like this, yes, we can consider as this effective dielectric constant if you consider as K, okay, and K epsilon naught A by D we will write, and when you compare these two we will get the effective dielectric constant, what you will get the effective dielectric constant, K is equal to K1 K2 by, you can compare this one, 2K1 K2 by K1 plus K2. This is the effective dielectric constant, and this is what? Effective capacitance. Effective capacitance, right? Effective capacitance we find out. The capacitance formula is this one, and dielectric constant formula is. In our question they are asking to find the net capacitance, right? The net capacitance is this one. This is the net capacitance. Okay, and now let us continue. Okay, now we are going to discuss the next question, that is when the space between the plates of parallel plate capacitor filled with two slabs of dielectric constants K1 and K2. The space between the plates, these are the two plates. The space between the plates is filled with the two slabs. This is one slab, this is another slab. Their dielectric constants are K1 and K2, and each slab having area A by 2. Each slab, this is the first slab, this is the second slab. This slab has area A by 2. Total plate area is A. Total plate area is A. Look at here. The total plate area is A, and this area is A by 2, and this area is A by 2. Means half of the area occupied by the first dielectric slab, and the remaining half of the area is occupied by the second dielectric slab. And now I am going to find out the effective capacitance of this capacitor. Look at here, it was very simple to find out. Okay, and now for this what we have to do at here, these two capacitors are in which combination? We have to split it here. Okay, we have to split these two into two capacitors. Here the plates separation, width of this one and width of this one is the same, D. That means two dielectric slabs have the same width. In previous case it is different. Okay, and the first dielectric slab width is D by 2, and the second dielectric slab width is D by 2, right? And this one is K1 and this is K2, and this is end to end connection. This is plus if you will take, and the corresponding opposite side here we have to take minus, and plus minus one capacitor, and the next minus again, sorry, here plus will attract the minus, plus minus will be there, right? Here again plus will be there, and this is minus, right? The second plate is connected to the like this. This is series combination, we discussed all. Okay, let us see here. Now in this case this is a series combination. Now the parallel combination. What is a parallel combination in this case? Okay, this is the parallel combination. How it will be parallel combination, let us see, and how we can convert this into parallel combination, and how to find out the effective capacitance, that I am going to explain. It was very simple, remember that. It was this is positive, this plate is connected to positive, and this plate is connected to negative. And now up to here I will take as one capacitor, and this part is one capacitor and this part is one capacitor. This part connected to positive plate and this part is also connected to positive plate. Right, I will split like this. This is the first capacitor. Whose dielectric constant is K1. And this is the second capacitor. Its dielectric constant is K2. And this is connected to positive terminal and this is connected to negative terminal. Here the separation, this part we can take as one capacitor, whose capacitance is C1, and this part we will take as another capacitor. Okay, and these two parts, this is the positive plate. Okay, this part plate is connected to positive terminal, and this part plate is connected to positive terminal, and these two are connected to positive terminal, right? Upper parts. This is one part, this is one part. This one part is connected, these two parts are combinedly connected to positive terminal. These two parts divided into here separately like this, like this. And now this is the positive and this is the negative. And the negatives, this is connected to negative, and this is the total plate. Total plate area is A. Half of the area connected to negative and half of the area connected to negative, means the two plates are connected to negatives, and these two plates are connected to negative. Here we are splitting the one capacitor into two capacitors. Here the two plates, first terminals are connected to one point and second terminals are connected to another point. That means this is parallel combination. And first we have to write the capacitance formula for this one and for this one. And here area is what? Area is not A, it is A by 2, because only half of the plate area A by 2 is filled with the first dielectric, and the remaining A by 2 filled with the second dielectric. That's why area is A by 2. What is the separation between the two plates? Separation between the two plates is D. And here area is again A by 2, right, this part. And again the separation is D. And now effective capacitance I want to find out. First capacitor capacitance. Capacitance of first capacitor. Okay. Right, capacitance C1 is equal to what we write. And we have the formula for the C. C is equal to what? K epsilon naught A by D. Use this formula. C1 we write as K1 epsilon naught. A is A by 2, not A. Area is A by 2 here. And by D, right, here we are getting the K1 epsilon naught A by, this 2 goes to denominator, then 2D we will get. And similarly C2 we will write. C2 is again C2, it's this one, and K epsilon naught A by D formula. K is K2 at here, K2 epsilon naught, area is A by 2 by D. What you are getting it here? K2 epsilon naught A by 2D. Right? Now, it was very hot summer. I am making this lecture at 3 o'clock, right? Why switch off the fan and everything for the clear voice. Now it was very difficult to make the video. Okay, in any way, listen it here. Now I am trying to explain properly. And now let us continue. And for this, let us see. These two plates are connected in parallel now. Okay, parallel. All the first terminals are connected to one point and all the second terminals are connected to another point. In parallel combination, effective capacitance, net capacitance, how to find out? Right? Our question is that we have to find out the net capacitance. This one capacitor, capacitance we have to find out, right? And now for this, how to find out the net capacitance at here? Then the formula is what? In parallel combination, right? It was very simple. Cp is equal C1 plus C2, right? In parallel combination, we have to add Cp is equal, C1 is what? K1 epsilon naught A by 2D, right? This is the, and plus C2 is what? K2 epsilon naught A by 2D. Here we got. And now we can common the epsilon naught A by D. Then we will get K1 plus K2 by 2 into epsilon naught A by D. This is the formula for effective capacitance. If you consider that these two dielectric slabs combinedly act as one dielectric slab, then we write the C formula. If it is combinedly K we can consider, then C is equal to, we write as K epsilon naught A by D we write. Now what is the effective dielectric constant in this case? We can compare these two. When we will compare these two, then we will get the effective dielectric constant. Yes, that is K is equal to K1 plus K2 by 2. Okay, and let us go for another one more question, and this is an important question, previous CBSE question. Okay, and the last question is also previous CBSE question. Listen very carefully and practice properly. And now let us go for the another question. Okay, look at here. Now next question is that two capacitors of capacitances C1 and C2 are charged to potentials V1 and V2 separately, and they are connected so that charge flows from higher potential to lower potential. If the two capacitors connected in parallel such that the positive plate of one capacitor is connected to the positive plate of another capacitor, find the common potential and loss of energy. Okay, and now this is the previous CBSE question. It's a 5 marks question. Let us see here. It was very simple and to derive this one. And what is this? Okay, and look at here. There is a one capacitor. Let us go for the answer for this. Let us go for the answer. What they are asking the question in this. There are two capacitors, right? There are two capacitors. Firstly, we have the first capacitor whose capacitance is C1. Okay. And the next another capacitor whose capacitance is C2. And now this is open. Now we are not connecting these two capacitors, right? And now these two capacitors are charged. Okay, before connecting this one. Before connecting, for example, the charges on these two capacitors are Q1 and Q2 and potentials are V1 and V2. There are two capacitors are there. There are two capacitors. Two capacitors of capacitances C1 and C2 are charged to a potential V1 and V2. And these two capacitors are charged to a potentials V1 and V2. And look at here. This is the first capacitor and the second capacitor. There are two capacitors are there. Two capacitors of capacitances C1 and C2 charged to a potentials V1 and V2. This is the first capacitor whose capacitance is C1 and it is charged to a potential V1. The charge on stored on the first capacitor is Q1. Okay. Then, and this is the second capacitor. This is the second capacitor. The charge stored on it is Q2 and its capacitance is C2. It charged to a potential V2. And from this we write the Q1 formula is Q1 is equal, we know C is equal formula, C is equal to Q by V. Right, from this Q is equal to CV we write, C1 we write, C1 V1. And the charge stored on the second capacitor we write as Q2 is equal to C2 V2. Right, because C is equal to Q by V. From this we write Q is equal to CV. Right. And now what they are asking it here, there are two capacitors. We are charging first to certain potentials separately and then they are connected so that the charge flows from higher potential to lower potential. If the two capacitors are connected in parallel, now they are connected in parallel. Two capacitors are connected in parallel. Two capacitors are connected in parallel, right? Now we are connecting the two capacitors in parallel. Then after connecting the two capacitors in parallel, for example, here the charge is Q1. Okay, first capacitor C1 and this is positive terminal, this is negative terminal. And now this is the second capacitor. This is the positive terminal and this is negative terminal. And now we are connecting these two capacitors. Its capacitance is C2 and it is charged to a potential V2 and it is charged to a potential V1, right? And look at here. This is the first capacitor, capacitance C1, potential V1. Second capacitor C2, potential V2. Okay. And its potential is V2. And now they are connected in parallel in such a way that the positive terminals are connected together and the negative terminals are connected together. Okay. They are connected in parallel such that positive plate of one capacitor connected to the positive plate of another capacitor. Positive plate of first capacitor connected to the positive plate of another capacitor. Now these are connected in parallel. Now what happens if there is any excess charge is there? This is at high potential. If here it is at low potential. Then the charge flows from high potential to low potential until their potentials are equal. That means after some time they will acquire some common potential V, right? Because they are in parallel and in parallel combination potential is constant. And now here the new charge, to acquire the charge flows from higher potential to lower potential until their potentials are equal. That means, for example, when these two are connected, before connecting in parallel, the charge stored on the first capacitor Q1, charge stored on the second capacitor is Q2. After connecting in parallel, the charge stored on the first capacitor we can consider as Q1 dash, second capacitor is Q2 dash. Q I say. Why like this? Because here when we connect the two capacitors in parallel like this, then the charge flows from one plate to another plate, from high potential to low potential. When the charge flows from high potential to low potential, the charge will be changes on two capacitors, and the new charges on two capacitors are Q1 dash and Q2 dash, and they acquire the same potential. Why they acquire the same potential? Because they are connected in parallel, and that's why they acquire the common potential. And now that common potential formula I am going to derive. Before that, okay, when the two capacitors are connected in parallel, then they acquire charge flows from one capacitor to another capacitor until their potentials are equal, until they acquire common potential, until their potentials are equal, until their potentials are equal, right? And now let us see. For example, they acquire the common potential. The Q1 dash and Q2 dash are the new charges on two capacitors after connecting in parallel, right? After connecting in parallel. Yes. And common potential we can consider as, now how to write the Q1 dash formula? Okay, Q1 dash formula is what? Okay, the new charge on the first capacitor is Q1 dash, we write as C1 V1, but it is not V1 now, okay? And they acquire the common potential V, we write the common potential also, right? After connecting, Q1 dash and Q2 dash are the new charges on two capacitors after connecting in parallel, and V is the common potential. And then what we write the Q1 dash, right? We know Q1 dash. Do you know formula for Q? CV. Then Q1 dash, new charge on the first capacitor after connecting. Then C into V. C is C1 and potential is V1 not. It is V because they acquire the common potential. Potential on first capacitor is V, potential on second capacitor is also V. After connecting, they acquire the common potential. Before connecting, they have the potentials V1 and V2. And Q2 dash we write like this, C2 into V. Okay, but charge is conserved, we know, right? But charge is conserved means before connecting the two capacitors in parallel, right, how much charge will be there? After connecting also same charge will be there. Means total charge before connecting is Q1 plus Q2. After connecting is Q1 dash plus Q2 dash. Right? Before connecting the two capacitors in parallel, the charges stored on the first capacitor Q1, second capacitor Q2, total is Q1 plus Q2. And after connecting the two capacitors in parallel, the charges are Q1 dash and Q2 dash. Then Q1 plus Q2 equal to Q1 dash plus Q2 dash. Right, then Q1 formula we know C1 V1 plus Q2 formula we know C2 V2, and Q1 dash we know, here we got Q1 Q2 Q1 dash Q2 dash, right? C1 V plus C2 V. On the right side we can common the V, and then we will get C1 plus C2. Then V formula we will get as C1 V1 plus C2 V2 by C1 plus C2. This is the formula for common potential, right? What is the common potential? If they connected in the parallel, then find the common potential. This is the formula for the common potential, right? What is V at here? V is the common potential, right? And V1, V2 are what? V1 V2 are the potentials of two capacitors before connecting them in parallel. And now they are also asking to find out the loss of energy, right? Okay, now I am going to rub this. How to find out the loss of energy? How we can find out the loss of energy? It was very simple. Before connecting the capacitors in parallel, we have to find out the total energy. After connecting the two capacitors in parallel, again we have to find out the total energy, and then there is some loss of energy will be there. When we connect these two capacitors in parallel, the charge flows from one capacitor to another capacitor, from higher potential to lower potential. During that, some of the energy will appear in the form of heat, okay, and due to that some energy loss will occurs. That means initial energy is not equal to final energy. Let us see. And now before connecting the two capacitors in parallel and find initial total energy, we can find out, right? Initial energy, initial total energy, initial energy, right? Initial energy is Ui, that is the energy stored on the first capacitor. First capacitor, capacitance C1 and potential V1. Before connecting, the energy stored is half C1 V1 square, right? And plus energy stored on the second capacitor is second capacitor, capacitance C2 and potential V2, half C2 V2 square. And now final energy we can write. Final energy, right? Final energy is what? After connecting in parallel. After connecting in parallel. Okay. After connecting in parallel. After connecting two capacitors. Two capacitors in parallel, right? Now let us see what you will get. And now for this, the final energy is after connecting they acquire the common potential. That's well the initial energy stored in the first capacitor is half C1 V square. Energy stored in the capacitor, we derived the formula, right? Half CV square. And the first capacitor half C1 V square, because potential is V. And the second capacitor energy stored is half C2 V square, right? Because V is the same at here, V1 V2 is not there. After connecting the two capacitors in parallel, they acquire the common potential. Then we will get the final energy as half into C1 plus C2 into V square we will get. And now UF is equal to what we want to know? We want to find out the loss of energy, right? Loss of energy. Loss of energy is delta U. It is equal to initial energy minus final energy. Initially large energy is there, and after connecting them in parallel some energy loss occurs. That's where final energy is less. Ui greater than UF. Initial energy is more, that's why some energy is lost. And the loss of energy is equal to Ui is half C1 V1 square plus half C2 V2 square minus UF is half C1 plus C2 into V square we write. And now when we simplify this one, and how to simplify this? Before going to simplify, we have to write the formula for the V common potential that we derived in the here in equation 1, and from equation 1 we write the formula for V, that is C1 V1 plus C2 V2 by C1 plus C2 whole square, right? And this we are writing from where? This we are writing from equation. This we are writing from equation 1, right? From equation 1 V formula we are writing. Now let us simplify this. Here A plus B whole square formula you can apply, and C1 plus C2 whole square LCM you can do. Okay, C1 plus C2 whole square, here 1 C1 plus C2 cancel, and you can simplify this, and I am writing the final formula directly, that you will get as half C1 C2 by C1 plus C2 into V1 minus V2 whole square we will get. This is the loss of energy. This is equation 2. Yourself you can simplify. Okay, and now this is the question, and now what is our question? Question is that to find the common potential and the loss of energy, right? We derived the formula for the common potential and loss of energy. Two capacitors of capacitances C1 and C2 and charged to potential V1 and V2. When they connected in the parallel, they acquire the common potential. The formula for the common potential is this one. And when they will connected in the parallel, when charge flows from one capacitor to another capacitor until their potentials are equal, during that some of the energy loss will occur. The loss of energy formula delta U is equal to half C1 C2 by C1 plus C2 into V1 minus V2 whole square. This is the case. And the next, some note point I will give, that is, if in this case we are connecting the two capacitors in parallel in such a way that the positive plate of first capacitor connected to the positive plate of second capacitor. But if not, I am telling that what we are doing it here, if two capacitors, in above case, if two capacitors connected in parallel in such a way and positive and negatives are connected together, okay, what happening, how we are connecting in parallel plate, they are connected in such a way that the negative plate of one capacitor is connected to the positive plate of another capacitor, connected in parallel in such a way positive plate of one capacitor connected to negative plate of another capacitor, then what is the formula for the common potential and then what is the formula for the loss of energy. Look at here what happening. This is the first capacitor whose capacitance is C1 and potential is V1, and this is the second capacitor whose capacitance is C2 and potential is V2, and now these two are connected in parallel. Okay, how we will connect them in parallel, right? And now look at here, I will draw this diagram. Firstly, there is the first capacitor, capacitance C1, potential V1. Second capacitor, capacitance C2, potential V2. And now these two are connected in parallel like this, and C1, C2. When we connect them in parallel, they acquire the common potential, right? The common potential is V. Common potential is V. But here, the positive plate of one capacitor connected to the negative of another, like this. Negative is connected to positive. In the previous case, plus connected to plus, minus connected to minus. But at that moment, we derived the common potential and the loss of energy. Here, the case is that plus connected to minus, minus connected to plus. Then what is the common potential and what is the loss of energy? It was very simple. The second one is, we can take as minus V2. Then the common potential formula we write as like this. Common potential, right? First common potential we will go. We will go for the common potential. The common potential formula is, right, C1 V1 minus C2 V2 by C1 plus C2. This is the common potential. What happening it here? Here what we are doing it here? V2 is replaced by minus V2, that's all. Okay, V2 is replaced with, second one is changed terminals, instead of plus minus, that's why here common potential we have write minus. And loss of energy, in previous case formula is what, this one, V2 we have write minus, minus into minus plus you will get, then the loss of energy we will get as half C1 C2 by C1 plus C2 into V1 plus V2 whole square, right? And this is the loss of energy. Okay, and now this is the previous CBSE 5 marks question. Okay, and thank you for watching my lectures. If you have any doubt, you can contact me. I will give one question. Okay, further solution you can write, answer you can write in the comment. Okay, and you can also comment how my lecture is there. Okay, and like my lectures, share and subscribe. I will give the one question at the ending. Okay, everyone look at here. Your question is ready, right? You have to answer this question. Okay, and you can answer your question, my question answer you can write in the comment box, right? And what is our question? A parallel plate of capacitor, a parallel plate capacitor of capacitance C is charged to a potential V. Another capacitor of capacitance 2C charged to a potential 2V. First capacitor capacitance C charged to potential V. Second capacitor capacitance 2C charged to potential 2V. And these two capacitors are connected in parallel to each other in such a way that positive terminals of one capacitor is connected to negative terminal of other capacitor. Now our question, common potential and final energy of configuration. This is my question and try to solve it.